Hello everyone, I am Uttam Satpute, Professor Electrical Engineering Department at Dr. D.Y. Patil Pratishtha's College of Engineering, Sanakinagar, Kolhapur. This is video number 3 on Unit 5, Optimal Power System Operation. And in this video, we shall have a numerical on economical load scheduling without transmission loss. I will take a problem that is there in the question bank. So this is the problem. The fuel costs of two power plants, they are given the fuel costs. The one C1 is equal to 100 plus 2 P1 plus 0.005 P1 square. This is in rupees per hour, and another fuel cost is given as 200 plus 2p2 plus 0.01 p2 square. It is also rupees per hour. Now the question is find economical load scheduling, economical economical load scheduling for a load of for a load of for a load of 450 megawatt and find the loss of economy, find loss of economy for deviation. So this is a question bank problem. Okay, so let us start the solution. Now we have derived one condition in the previous video, that is for economical load scheduling the incremental cost. So this is the concept what I am using here, the concept what we have, the condition, the criteria what we have derived in the previous video. That criteria I'm just repeating just to understand this problem. So the criteria we have derived, it is incremental cost, that is DCI divided by DPI or DPGI you can call, it is to be equal to lambda. So this is the criteria we have derived, uh, and here we are not considering transmission loss. So this is the criteria, what we call it as equal incremental cost criteria. This is incremental cost criteria, incremental cost. So what it states that for economical load scheduling, the incremental cost of all the power plants should be equal and equal to lambda. And this we call it as coordinate equation. And this coordinate equation we can solve it by various methods. So there are various methods available we can adopt. Uh, the one, it is graphical method we can adopt. I will not explain this in this problem, but we can adopt this method. Other one is analytical, and analytical method is preferred when the cost function is quadratic. But if the cost function, now in the present case our cost function is quadratic, so we can adopt this analytical method, and another method, it is iterative. So for if we are writing any program, if we are using computer for doing this economical load dispatch, then we can adopt this iterative technique. So now I'm adopting this analytical method to solve this problem, and this is the coordinate equation what I'm going to solve. So this is the concept you have to understand. Now let us start our solution. Okay, so now, okay. Now what we have to do, uh, first let us find the incremental cost. Now C1 is given, let us differentiate, let us find the incremental cost of plant P1. This is the incremental cost. So C1 is given, I'm going to differentiate with respect to P1. So what is C1 is given? C1, it is given as 100 plus 2P1 plus 0.00505 P1 square. So I differentiate this equation with respect to P1. So what I get here, I'll get now differentiation of this 100, it will be 0. And now when you differentiate this term, you will get 2, 2 plus, now you differentiate this third term 0.005 into P1 square. When you differentiate P1 square, you will get 2 into P1, and already this 0.005 is there. So we will get this as 0.01 P1. So this is the incremental cost we have determined for plant P1. Now find the incremental cost, find the incremental cost for second plant. Now differentiate the second cost function. Now C2 is already given, it has 200, here it is 200 C2, okay, and 2 P2 is there, and in this place we have here 0.01 P1 square. So when you differentiate now this C2, you will get again 2 plus 0.01 into 2, you will get it as 0.02 P2. Now we can see this is the incremental cost. So you can write the unit if you want, rupees per megawatt hour, and this is also rupees per megawatt hour, because the power P1 and P2, they are, the units are in megawatt. Now now we will apply our criterion. What is the criterion? Criterion is that these two costs should be equal. The incremental cost dC1 by dP1 and dC2 by dP2 should be equal and equal to lambda. Okay, so what we will take, let this be equal to lambda. Let this be equal to lambda. This is incremental cost. Now, from this equation, what I can write, I will get P1. P1 equal to lambda is there on this side. So these two I will take on this side minus lambda minus 2 divided by 0.01, and similarly I'll get P2 from this equation. I'll get P2 equal to lambda minus 2 divided by 0.02. So from these incremental cost equations, I have obtained P1 and P2. Now we will apply the constraint function. So what is the constraint function? The constraint function is that the generations should be equal to load, but we know that P1 plus P2, it should be equal to PD. Now PD, the load what they have given, this PD value they have given, the load we have, it is 450 megawatt. Okay, so now substitute the equations over here. Lambda minus 2 divided by 0.01 plus lambda minus 2 0.02 equal to 450. Now you can take a LCM over here. So if you take LCM, it will be 0.01 into 0.02 divided by 0.02 into lambda minus 2 plus 0.01 into lambda minus 2 equal to 450. Now, when you solve this equation, now you solve this equation for lambda. So, okay, I will do it over here for you. Now you can see here uh, this 0.01 into lambda and 0.01 into lambda, it will be 0.03 lambda. Okay, and it is equal to, so it is equal to 450 into 0.01 into 0.02 minus, sorry, plus 2 into 0.02 plus 2 into 0.01. And from this equation, when you calculate lambda, the lambda will come out to be 5. You just please check out what will be the unit of this lambda. It is incremental cost, so it is rupees per megawatt hour. So what we find that for economical load scheduling, for both the plants, their incremental cost should be 5 rupees per megawatt hour. Okay, now from this equation, let us calculate. Now what I'll do, this lambda, whatever I have find out, I will substitute here in this equation, and this equation, and I will find out what is P1 and P2. So now we have a lambda value which is equal to 5. Now I will use the equation P1. The P1 is lambda minus 2 divided by 0.01, and now 5 you substitute lambda value, substitute 5 minus 2 divided by 0.01, this will come out to be 300 megawatt. So we have determined that the plant 1 should generate 300 megawatt, and similarly for P2 we can substitute, we can have this equation lambda minus 2 divided by 0.02, which is equal to 5 minus 2 divided by 0.02. Now this it will come out to be 150 megawatt. Now what we have determined here, we have determined the economical load scheduling. That is, we have two plants, the plant number 1 and plant number 2, and what are given to us, we are given the performance curve. Now cost functions C1 and C2 are given, means cost curve. C1, it is nothing but the performance curve, that is fuel cost curve, and C2, it is also given the fuel cost curve, and these two plants, they are connected and they are supplied to a load of 450 megawatt. Now for economical load scheduling, we say that this plant should generate 300 megawatt and this plant should generate 150 megawatt. Then we can have an economical generation. The generation cost will be minimum. So we have done one part over here, that is, we have find out the economical load scheduling. Now we have to calculate the the second part. The second part, it is the uh, loss of economy. Loss of economy if there is a deviation. Loss of economy for deviation. Now this means that if instead of generating 300 megawatt, if it deviates from this, say if we generate say 225 megawatt. Okay. Now, if you think that they are doing equal sharing, that is 255, 225 megawatt, 225 megawatt, means they are deviating from their economical scheduling. Then there will be loss. There will be loss. Then how much loss? That is what we call it as loss of economy. So how to calculate the loss of economy? Now there is a equation. I'm not giving this here, not deriving this equation. Now I'm giving this equation. Please remember this equation. So it is lambda square epsilon square divided by A. This is the equation to calculate the loss of economy. Now what is lambda? Lambda is already we know it is 5. Epsilon, it is a deviation in the incremental cost curve that we will substitute later. Now A is the average slope. So let us first calculate A value, the average slope. Average slope, how to calculate the average slope? Now we have find out the incremental costs, that is dC1 by dP1. I think it is 2 plus 0.01 P1 we have find out, and the incremental cost for second plant dC2 by dP2 we have find out it is 2 plus 0.02 P2. Now this is the slope of this first power plant incremental uh, uh, plant 1 and plant 2. This is the slope. Now we have to find the average slope. So average slope is 0.01 plus 0.02 divided by 2. So we will get this value as 0.015. Okay, now substituting this value in this equation, delta F equal to 5 square. Now 5, it is the lambda value is 5, so square is, and let us take this epsilon as 0.01, that is the deviation. So this is 0.01 I will take, divided by 0.015. So this value, uh, I just calculate this value. 1 minute, I'll calculate. Okay, so this value is coming out to be 0.01667. The unit is rupees per hour. So for any deviation, uh, or for any unit deviation, so we will get this, uh, for any unit power deviation, we get this loss of economy 0.1667 rupees per hour. Okay, so this is up to this problem. Okay, thank you very much.